Hello everyone, my name is Victor Fogos da Rocha, and today I'm going to present the paper called Benchmarking SRGAN-Upscaled YOLO for an erased object detection in aerial imagery. The motivation of this paper is it's very hard in the computer vision domain to detect small objects, especially the aerial ones, because of the variability in the captures sensors. For example, the cameras in the drones and the helicopters, and also in satellites that can vary a lot the quality of the image and the size, of course, of the objects. Like, for example, small objects can be considered like having less than 50 pixels, and of course the dataset imbalancing. So when we have different quantities of images or objects, or the annotations reference of each object categories, it's very hard to train a model that can combine the quality on the detection and on the recognition classification, for example. So this work presents a few contributions, like the benchmark of 10 different variations of YOLO, the YOLO object detection model on the DOTA dataset, the integration or even the usage of as super resolution GAN to generate images, the analysis of different values or scale factors, or in our case to upscale the image, so to generate new images, and the introduction of a frugality score value to better analyze how a model the behavior of the specific model from a specific metric on different hardwares in different platforms. In relation to our related works, we've used the as I said before, the SRGAN, a super resolution method to generate new image with a higher quality, especially to try to improving the small object detection when training our models. But which models? In our case, the YOLO family, because it's one-shot efficient, one-shot model, one-shot object detection. So we have only one step to gather the object positions on the image to detect it, and it's also very efficient for real-time aerial tasks. The frugality metric just gives us a balance between the accuracy and the efficiency. Here we presented our workflow, the generation of the image, the object detections in our benchmarks, and then the analysis of the frugality. But what's frugality? Frugality, it's a metric, as I said before, to better analyze how a specific metric, like for example the mean average precision in your case, can have its behavior affected by a specific model in different scenarios, different hardwares. So in relation to our scenarios, we have split it in our works into three different scenarios. The first one, when we use the original data to train and also to evaluate our models, the 10 models in the benchmark. The second scenario, when we generated the image, so we use the generated image and to train and evaluate the models. And the third scenario is when we use the generated image to train our models, the 10 models, and then we use the original image as a cross-validation dataset process to evaluate our original image on detections. So in our methodology, basically when you split it into two steps. The first one, we needed to compress the image to generate the low resolution image, and then this image can be upscaled by a scale factor. For example, in the image of the figure 4a, we just use the cubic interpolation, a standard method, to downsample the image, the original image, in a high resolution. To then, with the lowest resolution, we can upscale it, so we can generate a new image with an upscaled factor by the SRGAN. And the second step in the pipeline is we just use as the previous slide. We can split it into different scenarios. The first one, when you use the original image to train our models and to evaluate its models, and also to generate a new image to the training and to the evaluation. Then we analyze the first scenario only as a baseline. The first scenario, original image to train and original image to evaluate. The second one, again, the generated image to train and to evaluate, and the third one, the cross evaluation. So using generated image and evaluating the models with the original ones. Okay, our dataset. Why we choose the data? Because it's very popular in this domain, and it presents a great challenge, especially because there is a great imbalancing between the categories, the object categories, and almost 60% of the objects present less than 50 pixels, so it's very hard to detect it. To train our models, we've used the cluster provided by the Université Sorbonne Paris du Nord, and we've also used the data augmentation, in this case to call it mosaic augmentation, to fuse different types of objects detections, different objects annotations during the training process to better increase its performance, the model's performance. And we also have used the evaluation metrics to evaluate the SRGAN as the quality of the image generated, and also the classification in the end of the models. So the first results, after almost 400 epochs, we've got the SRGAN models to different scale factors, and in our case the 2, 4, and 5 scale factor values. And we've got the best result when we upscale the models, the low resolution models, and generated new images when using the scale factor equals 2, getting a better quality on its image when using the scale factors equals 2. Here is an example in the figure 8, but as you can see here, even with an image with a great quality, the SRGAN can produce some artifacts in the image that can make it more difficult to detect the models. That can make it more difficult to the models to detect the small objects. Also, we have observed that with scale vectors like 4 and 5, so greater than 2, the small objects start to be fused. So the small objects start to lose its information, specific information, as we can see here in the figure 9. They start to make basically one object. So the first result, we've observed that in our case we got a small increase in the mean precision for the scale factors equal to, but we got an increase on the mean average precision for different intervals of values. But we can observe an increase in the recall for different scenarios. Here, when we observe the different scenarios for different scale factors, we can observe that for a greater resolution, we got a best performance for, here. The final results, we can present our model, our best YOLO benchmarks model. We got the YOLO V5 transformer present the best increase on its performance, with mean average precision improvement by by almost 3%, with scale factor equals to for our higher resolution. But we observed that SRGAN can help on the increase of the performance, but only for a small value of scale factor. When analyze the results of the frugality, we observe that for different scenarios that the frugality is stable for different challenges or for different types of simulated hardware. So it's stable even with the increase of the performance of our models. The positive points are the SRGAN improves the YOLO, especially for small object detections. We provide a benchmark that is stronger as a baseline for future reworks. The negative points or its limitation is a high scale factor, as I said before, merge small objects, so make it this type of object worse to detect, and it shows that the dataset imbalancing factors more the minor class on its recognition. Our summary, as I said before, our best scenario, the increase of the quality on the detection, the small object detection, the YOLO V5 transformer with the scale factors equals to 2. The frugality ensures our deployability on embedded systems, and for future works, we planning to use the newest architectures based on the YOLO, and also alternatives to GANs for new super resolution GANs. Thanks so much for the Labicon Iris and for the Agence Nationale de la Recherche Scientifique in France. Thanks so much, and also for the DPN, a few reference, and so feel free to make your questions, and thanks so much for your attention.